Hello everyone. So, good afternoon. My name is Raj Sharma and I am presenting my phase 1 work on estimating remaining useful life and the state of health of EV batteries using hybrid frameworks. I am working under the mentorship of Dr. Sandeep Patale. And so let's start with some motivation and introduction. As we transition to electric vehicles, a reliable battery life prediction or health prediction is important. And as we know that lithium ion batteries degrades not non-linearly, so it leads to some critical challenges like safety risk and economic risks. Like when we overestimate the battery health, it leads to some charging issues or thermal issues. And when we underestimate the health, we retire good batteries too early. So my objective is to build a lightweight framework that is safe, accurate, and simple enough to run on small or standard chips like microcontrollers, and specifically on a constrained battery management system (BMS). In literature review, I found these two approaches or extremes. Like first one is a model-based approach where they use to calculate some complex physics equation and partial differential equation. It is accurate but is computationally very heavy for standard BMSs. And data-driven approaches like black boxes, like some transformers and LSTM. These are highly accurate but require large amount of data set, so there is clearly a gap. Although there exists some pins also which rely on complex partial differential equation and use static weight for load balancing, but I found there is lack of lightweight hybrid models. And my thesis is about this part only. Like I'm going to build a lightweight hybrid model with combine these two, like simple ODs and good deep learning models. And I'm also going to do some like this dynamic loss balancing. So let's start. As a for a problem statement, my objective is to uh, estimate state of health accurately. And my challenge is also same, like the prediction should follow the thermodynamic and physics laws and provide good accuracy. For regularizer, I'm not using heavy equation. Instead, I'm used two simple ordinary differential equations. First is logistic model, which capture the degradation, how degradation saturates over time. Another one is double exponential model, which crucial to capture the knee points. Knee point is the moment where the battery suddenly ages very fast. So these two constants help me to predict my results with good accuracy. This is the solution strategy and proposed architecture. So here the data pipeline, where we input our data from these two data sets. And for feature engineering, we are using Setfit Golay filtering to reduce the noise. For extraction, we are using ICA peaks. And here GRU is our backbone. We are using GRU because this is simpler than LSTM, and we can deploy this like on some simple BMS systems also. So like it is the lower the parameter counts, making it efficient on edge deployment or some edge compatible devices deployment and battery management systems. And the challenges are there. Here the manual tuning will be required, but I proposed like my solution is I'm using adaptive weighting. Like this is statical method where the network automatically learns how much to trust on physics and versus how much to trust on data during the training, and remove the need of manual guessing. That data in the data set description, I'm like using these two data set with different capabilities. First one is NASA, coming from NASA, and this dataset is noisy. It tests the model robustness. And another one is Calki dataset. It shows the knee point effects and help us to generalize our model. So with complex aging patterns. in in this in this part, to prove this work, I have some strict benchmarking metrics. First one is the model based baseline, which where I'm using some simple curve fitting, and another one is data driven baseline, which is standard grus, and I will validate this using loco and cross loco and some cross domain checks, where we train on one data set and test on another one. And uh, and uh, I will it help us to like generalize the result with different chemistries and other stuff. Resource feasibility, this is the key part of this project. My proposed model used approximately 15,000 parameter, which is significantly smaller than the large transformer models. This allows the models to fit within less than 128 kb flash memory, making this perfectly suitable for real-time use for standard microcontrollers. In summary, we address some trade-offs between accurate models and white box models. We propose lightweight hybrid approaches using GRUs and simple ODEs. In contribution, we the model is practical with no heavy partial differential equation. Also, we are doing adaptive weighting and robust. The model is robust to noise. In proposed roadmap, I will going to implement my work build curve fitting baseline and hybrid GRU model, and evaluate by conduct an ablation study and to quantify my improvement and data efficiency. I hypothesize that my physics informed model will perform better than standard AI, even when we reduce the training data set to just 20%. So hope for the good. Let's start. Thank you all.